Hello, everyone. Today we're going to solve the Leet code question, search insert position. Now, this is a really fun video. Actually, this is the most fun that I had creating a video, just because initially I thought it wasn't going to be too great. There was kind of two approaches to this question. You can perform a linear search or you can perform binary search. As part of kind of like a little bit of a teaser, this is just something that you'll be noticing with down the line within this video, or actually within part 2 of this video, because first we're going to tackle linear search, then binary search. You may know that I like to show test cases. I like to show kind of like the logic as you kind of go through the different test cases so that you can kind of visualize what's going on with our code. But then I realized if I do it for binary search, it might be kind of difficult to show that logic. I have to move a lot of pointers. There's the left pointer, there's the middle pointer, there's the right pointer. There's a lot of stuff to show. And I was initially trying to do it just with comments, but that was really rough. I realized I should probably use the debug tools, but I felt there it wasn't visualized as great as I wanted it to be. So then in this case, for this example, I took some time to create a function that would go ahead and spit out the visualization of our binary search. And what's nice about this is you can see that, let's say, for example, I have my list of numbers, 1, 3, 5, 6, 7, 7, 7, 9. And let's say I'm searching for the number 8. So if you're not familiar with binary search, I strongly recommend watching this video and in the next video, just because we're going to go through it. But you can see that we can, in the videos, we're actually going to visualize each of the steps. So this is going to be the first step of binary search, the second step, the third step, fourth step, fifth step. And then by this step, it's solved. So within 5 steps of binary search, we're able to solve where I should insert the number if it's not found. If it is found, this will also kind of work in that. This will also work for that situation as well. But once again, this is a little bit of a teaser. This is when we get to the binary search section. I just kind of wanted to show off that tool initially so that hopefully you'll stay for, if not this video, at least part 2, and in which case we go over binary search. But enough of that teaser. Let's go back to the original question and see what it's asking us. So for this question, what we want to do is we want to we're going to be given a sorted array. So we're going to be given a vector of integers, and we're going to be given a target value or a key value. And what we want to do is we want to return the index where we found it. If we do find our key within our vector, then we're going to go ahead and return the index where it's found. Pretty straightforward. However, what if it's not found? If it's not found, we don't return -1 to indicate that it's just not present. What we're going to do is we're going to return the index where it should be placed in order for it to be ordered. So in this case, let's go through some test examples. So for example, I see my vector of 1, 3, 5, 6, and my key is 5. Well, I know that the key exists in here, right? If I were to perform linear search, I could just go forward, compare them to see if they're my key, they're not my key. And then once I get to this part, I see that that's my key. So I can just return the index 2 because I did find my key at index 2. That one's really, really straightforward. Let's continue. So what if my target is, or my key is 2 and my key is not in the list? So in that case, that's where we want to return where we should stick it in, where we should insert the key into our list in order to keep it ordered. So what we're going to do is we're going to go ahead and iterate through the list. Notice we don't want to insert it here, but we want to insert it before this 3. And so what we're going to do is we're going to insert our key at index 1. And we'll go through the logic, but essentially, if the current element that we're looking through is smaller than your target, then you keep going, right? So you keep going until the next value. But as soon as the current element is bigger than your target, that's exactly where you want to insert your key. So I would want to insert the 2 right in here, right in between here. So you can imagine I have 1, 3, 5, 6, and then and our key is 2, key is equal to 2. So then this value is smaller than my key, so I don't really care. This value is the first value that's bigger. So this is where I would want to insert the 2. Right, and which index is this? This is at index 1, right? So this is index 0, this is now index 1, and that's why we return an output of 1. Now going back to the next logic, we can imagine that we have a target or a key that's greater than all of our values. So in that instance, we're going to go ahead and we can see that we want to insert it at the very end. But how does that work? Well, what we're going to do is if we're performing a linear search, we would go ahead and see that the current element is smaller than my target, or smaller than my key. So then I'm going to keep going then this value is smaller than my key. So keep iterating. This is smaller than my key, keep iterating. This is smaller than my key, keep iterating. So at no point in my list did any of the current elements beat out my target. So I know not to, so I never returned an index at that point. So what I have to check is once I'm done iterating through the entire list, I have to check, okay, well, if my target is greater, if my target is greater than the last value on my list, I can go ahead and return essentially this this index, which is going to be one after the last index. So this is going to be size -1. So I'm going to return size, right? So that's just something to consider. You could do that check at the beginning, actually, now that I think about it. So you could just kind of get that out of the way, just because all of these values within our list are going to be in sorted order. That's one thing that they're going to provide to us. So notice they're going to give it to us in ascending order. So that really does help us out a lot. It eliminates the need to go through linear search. And what it allows us to do is, since we have the sort for free, we're able to kind of run this problem in O of log n time complexity, not for linear search. Linear search is going to be linear time complexity, right? So it's going to be it's going to be linear because I have to iterate through all of the elements within my list. But whenever you have a sorted list, you can always perform binary search. And that's really what they're asking us here. They're asking us, hey, can you go ahead and perform binary search in this problem? And we can, but that's going to be for part 2. Part 1 is just going to be a simple linear search to make sure everyone feels comfortable with this. And then afterwards, in part 2, we're going to go ahead and talk about binary search, kind of how to use it, how to implement it, and then also tools to visualize it. So now that we kind of understand that, what we're going to do is let's go over the pseudocode. So what we want to do is we're going to perform linear search. Once again, this is O of n time complexity. And so we're going to go ahead and traverse the vector. And there's really 3 things to consider. Number 1, if our current element matches the target. So if we find a match, like let's say if my key is 1, the first time I go in here, the current element is my key. So then I'm going to go ahead and say, well, I found it. I can go ahead and just return that index, right? So if at any point the current element matches the target, we know we found our key, and we can go ahead and return the current index, right? So that's the first step. That's one's pretty straightforward. Now, what happens if the current element is smaller than my target? Well, we discussed that in this case, right? So if my current element is smaller than my target or smaller than my key, then I just keep going. I just keep moving forward. There's really nothing kind of interesting about it. That's it. And then what's the third case? The third case is the first time. So the first time that my current element is greater than my target. So the first time we have an element that's bigger than your target, that's exactly where we want to insert the target. Okay, so that's where we would go ahead and return, and we would say that's the index I want to insert it at. Okay, because if we find a value that's greater and we never found one that was equal, that means it didn't exist, right? It's in sorted order, so we never went ahead and found that value. You can imagine kind of like this, going back to 2. So this value was smaller, and then suddenly I found a bigger value, 3. So because they're in sorted order, I'm not going to find it 2, right? I can't expect any values to the right of 3 to be smaller because it's in ascending order. So those are really the steps that we want to perform while we're traversing the vector or iterating through the vector. And then the last case is, or it could be at the beginning, just depends how you want to set it up. An edge case is, what if the target is greater than all the values on the list? Just like in this third case. Well, in that third case, what we want to do is we should insert it at the very, very end of our list. We should append it to our list, essentially. So what we would do is we would return not an index within our vector, but the index right after our vector, which is the same thing as our size, right? So that's pretty much it. That's the method for kind of going through this logic. If you need to, I strongly recommend kind of reviewing it if you don't feel comfortable with the linear search approach. But this one should be, I want to say, pretty comfortable, at least starting off. So let's go ahead and set this up. So we want to go ahead and set up some convenient variables like our current value. And we also want to set up an index to insert. So this is if we don't find it. This is where it should go. Okay. And then now let's go ahead and iterate through our vector. Okay. We're going to go ahead and use our trusty for loop. Our index. Index is less than my vector size. Go ahead and increment. And for convenience, we're going to go ahead and set up our current element, right, or current value. So the current value is really just nums at the index, at the current index. That's pretty much it there. Once we have this value, we're able to kind of compare it against our target. So what are the comparisons we want to make? We want to compare if it's equal, if the current element is smaller, or if the current element is greater than the target. So those are three options. Let's go ahead and start off with equals. If the current element or current value is equal to my target, so then I found the key. All we need to do is we need to return the current index. So exactly where I found it right now, this current index, I'm going to go ahead and return it because that's the place where I found it. So return location where I found the key. It's pretty straightforward. Now, what if I want to run into this situation where the current value is smaller, or sorry, the current value is smaller than my target? Well, we want to continue to the next iteration and continue to the next iteration and so forth. So if my current value is less than my target, so this is the case where we keep going. The way we do that is we can go ahead and just write continue, or we could just leave it as blank. Really, we don't. So it's within our loop. It's going to only trigger one of the bodies within our multi-way if statement. So this is not necessary, but it's more explicit to say, keep going. Keep it. Now, what if? So I could write else here, or I can write else if I want to be explicit. Let's just write else in this case. So if the current value is greater than the target, so this is the first time that we see a value bigger than our target. So this is exactly where we want to stick in our key. So what we're going to do is we want to mark this as our index to insert. And that's going to be the current index. And then what we're going to do is we're going to break out of here. We don't want to keep iterating. We found exactly where we want to insert it. So we're going to go ahead and break out of here. And that's it. So there's a few kind of options, or there's kind of two ways to exit. If you find the key, you can exit this way, or if you find where to, insert it, because you found a greater value, you would go ahead and just break out. Now, what about the last edge case, right? What did we say about this edge case? If the target is greater than all the values. So how do I know if the target is greater than all values? If target is greater than all values within our vector. So the way you know if that's the case is, since this is in sorted order, I can go ahead and just check if my target is greater than the last element. If it is, then I know it's greater than all the ones before it too, because it's in ascending order. So if that's the case, I just want to go ahead and stick it in at the very, very, very end. I essentially want to append it. So if our target is greater than the last element, so nums at the last index, then what we want to do is we want to say that the index to insert is really just not the last index, but it's going to be one after the last index. So we know that this is our last index. So one after the last index is just num.size. There we go. So append to vector, essentially. That's what it should be. It's not actually appending, but this is what we would want to do. And now that we have our logic set up, so we know exactly where we're going to where we found it or where we're going to insert, that's it. We're pretty much done. We just need to return that index. Return the index to insert. And that's really going to be our logic. It's very straightforward with the linear search. We're going to go through the binary search in just a bit. I just want to make sure that I didn't make any syntax errors while running this. Okay, perfect. So this looks good. I hope that this made sense. I didn't really spend too much time on it just because I know that this one's a little bit more straightforward, and I'm pretty excited, I got to say, about kind of going over this tool just to be able to visualize it. It's not really the best tool. It's just, I'm just very happy that I was able to kind of automate a part of it. And this just kind of shows as like engineers, whenever we have a problem, don't feel like you have to do everything manually. Sometimes you can like automate certain parts. And so I hope that this kind of incentivizes, or not incentivizes, but kind of inspires people to, try to find solutions as programmers to, to any kind of problem that you encounter. So that being said, thank you so much for watching this problem. Definitely recommend watching part 2, where we go over the binary search for this, and we actually meet the requirements of O of log n time complexity. Just because whenever you see this, just think of binary search for the most part. So thank you. Please comment below if you enjoyed it, and share your thoughts if you're excited for watching the next video as well. Thank you.